This is the seventh lecture of work energy powered. Okay, there will be 3 or 4 more lectures to finish off work energy power. So in this lecture, we discuss from question number 153 to question number 157. So just see the lectures. If there are any doubts, do mention in the comments. If there are any feedbacks, do mention them in the comments. Okay. In this question, what is being said is that there are two masses. Okay, and this masses is joined by a spring. That means the spring is attached to both of these masses, and the spring is compressed. Okay, the spring is compressed by delta L. Okay, the spring is compressed by delta L, and to keep this spring compressed, a rope is attached between the blocks. Okay, the job of this rope is to keep the spring compressed. Now the question is, what should be the minimum delta L? Delta L means the compression of the spring, such that when the spring or when the rope is burnt off, what will happen? This mass M will fly off. Okay. So what should be the minimum delta L, or what should be the minimum compression of the spring, such that when this block M flies off, it carries, or it is just enough to leave this bottom block above the ground. Okay, so what is happening out here is, see, this mass M. Okay, initially it was being compressed by, initially it was in compressed state. Okay, as soon as the rope is burnt off, what will happen? This mass will go above. So the mass is going above. Mass reached till this point. Okay, okay, so till reach up to its natural length. Okay, after reaching the natural length, will it stop? No, because it has some inherent velocity. No, so after this velocity, what will happen? This velocity will cause this mass to move more upward. So as soon as the mass moves upward from its natural length, what will happen? The spring goes from compression to elongation. Okay, the spring goes from compression to elongation. Okay, that means what? Out here, the spring force on the bottom block is downward and the spring force on the top block is upward. At natural length, okay, the spring force becomes 0. When the spring is stressed, what will happen? The spring force on the upward block would be downward and the spring force on the bottom block would be upward. So let this be natural length of the spring. Okay, this distance, or the distance by which the spring was initially compressed, is nothing but delta L. Okay, delta L. And let's say it was compressed by delta L. What will happen? It will go up, and after certain time it will stop, no? Because the velocity will be exhausted by the spring doing the work. Okay, so at maximum height or at maximum elongation, let's say it elongated by distance x. Okay, now the question is asking what is the minimum value of delta L such that when the maximum elongation occurs, okay, the spring force out here is just enough to lift this bottom block from the ground. Okay, so for minimum value of delta L, at maximum value of spring, what will happen? Maximum value of spring, velocity of this topmost block will be equals to 0. Understood this concept? Okay, for the minimum value of delta L, at a maximum value, at a maximum stress of the spring, or at maximum elongation of the spring, the mass or the velocity of topmost block would be 0. Can it be stretched? See, suppose if mass M was compressed more, what would happen? This x, or the value of this x, would be much more, but the M would jump off much higher, no? See, this M is going upward and the elongation is being stretched more upward. The spring force out here is becoming more and more, and this M is accelerating upward. So the question is, what should be the minimum value of delta L such that the block is just enough to lift up from the ground. So the condition is at maximum elongation of the spring. Okay, at maximum elongation of the spring, what is the spring force? The spring force is kx downward, and out here it is kx upward. So at maximum elongation of the spring force in upward direction should be or should balance out the gravity force acting on downward direction. Understood? Can it be greater? Can this be greater? Obviously this can be greater. If this is greater, the downward block or this block would just fly off, but that is not the question that has been asked. Understood? So at the minimum value of delta L, the condition for lifting up this block is at maximum stretch of the spring. Okay, the spring force on the bottommost block should be enough to lift up from the ground. So the spring force should be enough to counteract the gravity force. This is the concept that you are going to apply. Now simply apply work energy theorem. What is the velocity of block out here? Velocity of block is equals to 0 out here. Initial velocity of block. Out here the body or this body might have some velocity, but we are not interested at that. We are interested in what is the velocity at topmost point or maximum stretch of the spring. The velocity at maximum stretch of the spring would be equals to 0. After that, what will happen? The body would simply come down. Okay, so at maximum elongation of the spring, the velocity is equals to 0. So applying work energy theorem on on top block. Okay, initial velocity is equals to 0, final velocity is equals to 0. Change in kinetic energy is equals to 0. Okay, what are the total forces doing work on the top block? See, there are two forces acting on the top block. First one is the gravity force, second one is the spring force. So work done by gravity force is nothing but mg into what is the displacement. The displacement is delta L plus x, because mg is also acting in the entire journey, no? So delta L plus x. Okay, and this work would be minus. Why? Because gravity force is acting downward and displacement is happening in the opposite direction. And what is the work done by spring force? See, the work done by spring force is kx square, but out here the spring force will do work in two parts. See, from here, from this position to this position, the spring force will do positive work. Why? Because from here to here, the spring force is in this direction or upward direction, and the movement of this mass is also in upward direction. So from this position to this position, work done by spring is equals to half k into delta L square. Now from natural length to maximum elongation, the spring will do negative work. Why? Because after natural length, when the spring is being elongated, the spring force is in downward direction, whereas the displacement is in upward direction. So minus half kx square. This much is understood. So this is the first equation that we must apply. Okay. Now from this equation, I need to find out the value of x, and the value of x can be found out by this equation, where kx is equals to mg. That is the condition of the question, no? The minimum value of x such that the body or bottommost block gets lifted from the ground, or x is equals to mg by k, or x is equals to mg by k. Now simply apply this x in this equation out here and out here. Okay, so if you apply this equation, we'll get 0 is equals to minus mg into delta L minus mg into x. What is the value of x? Mg by k. Okay, plus half k delta L square minus half k into mg by k. The value of x is mg by k whole square. Okay, now this square mg and mg would become mg square. So this is nothing but mg square. Okay, out here k and k square would get cancelled. Okay, and it would become 1 by k and become mg square by K. This would become mg square by K. Okay. Now see out here. Acha, what we have to find out? We have to find out delta L. Fair and fine. So if we modify this equation or reorganize this equation, what do I get? See, out here, I can write this half K into delta L square first. Half K into delta L square. This is done. Acha. This mg square by K minus mg square by K and minus half mg square by K would become minus 3 by 2 mg square by K. Minus 3 by 2 mg square by K. Okay. And this minus mg delta L would come out here. Minus mg delta L. Okay. It was not necessary to cut out here. Now see, if you observe carefully, what do we need to find out? Acha, I have, can I write this mg delta L out here and minus 3 by 2 mg square by K in the right hand direction? I'm just interchanging these two positions. Okay, this is just equation solving. See, now this becomes a quadratic equation. Okay, but I need to find out the value of delta L. See, ax square minus bx, sorry, plus bx plus c is equals to 0. I need to find out the value of x, which is delta L out here. Okay, so simply before solving the quadratic equation, let's simply simplify the equation. I just multiply this entire equation by 2. What will happen? K into delta L square, okay, minus 2 mg delta L minus 3 mg square by K square by K. Okay. Now if I apply the roots of quadratic equation, where delta L is equals to minus b, so minus b is 2 mg plus minus under root of b square or minus 2 mg square or 4 mg whole square minus 4ac minus this minus and this minus would become plus, so plus 4. What is the value of a? The value of a is K into c is nothing but 3 mg square by K. 3 mg square by K divided by 2a. 2 into what is the value of a? K. Out here, see, look at this parameter out here. 4 into 3 is nothing but 12. So out here I can write 12. This K and this K would get cancelled. So this K and this K is getting cancelled. So let me open the bracket. Okay. So 12 mg square. Let me write it neatly. Okay. 12 mg square. 4 mg square plus 12 mg square is nothing but 16 mg square. So let me erase this one and write it 16 mg square. Okay, what is under root of 16 mg square? 4 mg. So delta L is nothing but 2 mg plus minus 4 mg by 2k. Okay, the value of delta L wouldn't be negative out here. Why? Because I have already taken minus sign to counteract this negative sign. Okay, so we erase the negative root of this equation. So the value of delta L would be 2 mg plus 4 mg, 6 mg by 2k or 3 mg by k, or is equals to 3 mg. 2 and 6 would get cancelled to become 3 mg by k. This is the first part of the equation. Okay, so this is the first part of the question. The second part of the question is asking if the compression of this spring, okay, suppose this spring was compressed by 7 mg by k. Instead of x, we'll use k out there. So that is easier to remember. Okay, if the compression of the spring was 7 mg by k, then the rope was burnt, what will happen? This mass will fly off. Okay, and after this mass has reached a height of mg by k, this block will lift off the ground. The question is asking what is the maximum height reached by the center of mass of this two block. Okay, So in order to analyze that, let us draw the diagram for three of those cases. The first case is when the spring was completely compressed by 7 mg by k. This is the first case. In the second case, we'll draw, see, after the rope has been burnt off, this mass will move upward. In the second diagram, we'll draw when the length of the spring has reached its natural length. Okay, this is the natural length of the spring. Okay, see, after cutting the spring, the mass has flung off, no? So after reaching the natural length, what will happen? This mass will again go upward. The third diagram is when this block has reached a height mg by k from the natural length of the spring. That means out here, the spring force is upward. Out here, there is no spring force because the spring is in natural length. And out here, the spring force is downward in upward block and upward in downward block. And remember, when the spring height reached mg by k, that means when the elongation of the spring is mg by k, that means what happens? This block just has started to rise from the floor. Okay, that means the contact from the floor has been broken out. Now what will happen? Both the block will move upward. Okay, so the question is asking what is the maximum height of the center of mass from this position to whatever is the maximum height of the center of mass. So let the maximum height, let the center of mass be out here. Okay, this is the center of mass of this body, H1. Now when this mass moved upward, the center of mass will also move upward, isn't it? So at from this position to this position, let's say the center of mass moved by h2 height. This is the center of mass of these two. Okay, then after h2 what will happen? Both this mass will move up, and what is the only force acting on these two masses after this? After this phase? Gravity. The spring force, we won't calculate the work done by spring force after this phase. Why? Because after this phase, as soon as the lower block lifts up from the ground, okay, the work done by the top block on this by the spring will be cancelled out by the work done by the spring on the bottom block. That means spring force becomes an internal force. As soon as this block lifts up from the ground, the springs becomes an internal force. Why? Because the work done on the topmost block by spring will be negative of work done on the bottom spring by the top spring. Okay, that means the same magnitude of work out here will be negative of same magnitude of work out here by the spring. That's why do not calculate the work done by spring after this block has been lifted off. Understood? So the first thing is first, this was the center of mass when the spring was completely compressed, and this was the center of mass when the lower block has just left the ground. Okay, so let's find out what is the difference between h2 minus h1. h2 minus h1 means nothing but, see, how much has this block traveled? 7 mg by k to natural position and mg by k. So total distance traveled by height this mass is nothing but 8 mg by k. Okay, so displacement of center of mass is nothing but mass of one, mass of upper body into displacement of upper body 8 mg by k plus mass of lower body into displacement of lower body divided by mass of upper body plus mass of lower body. See, from this position to this position, the displacement of lower body is 0. So that's why mass into 0. So x, or displacement of center of mass, would be 8 mg by k divided by 2, or 4 mg by k. Okay, so basically h2 minus h1 is nothing but 4 mg by k, or the center of mass from this position to this position has risen by 4 mg by k. Okay, understood this much? Now the second portion I have to find out, what is the velocity of center of mass out here? What is the velocity of center of mass out here? Why am I finding out this velocity of center of mass? Because after this body has risen upward, okay, the spring force wouldn't be doing any work. Okay, the only force that would be doing some work would be gravitational force, and it is a constant. So I can simply write v square is equals to u square plus 2as. or change in kinetic energy is equals to work done by all the forces, or half mv square minus 0 at topmost height. The velocity of center of mass would be 0 is equals to 2 into g into s. Understood? So I need to find out the velocity of center of mass at this point. Okay. So in order to find out the velocity of center of mass this point, I need to find out what was the velocity of topmost block. Okay, and the velocity of bottommost block. See, at this point when the elongation of spring is mg by k, the spring force just balances out the gravity force. Okay, so acceleration is infinitely small, so velocity is just starting to increase, so velocity is also is infinitely small or is equals to 0. Okay, now if I apply work energy theorem only on the top block from this position to this position, what will happen? Applying work energy theorem, applying work energy theorem on top block, on top block. Okay, if I apply work energy theorem on top block, what would I get? I would get half, what is the final kinetic energy? Half mv square. Okay, half mv square, mv square minus what is the initial kinetic energy? 0 minus 0. What are the forces doing work on the top block? Spring force, okay, and gravity force. But from this position to this position, the spring force does positive work, and from this position to this position, the spring force will do negative work. So from this one to this one, from h1 to mid position, the work done by spring force is positive, or half k, and x is nothing but 7 mg by k whole square. Okay, now from this position to this position, the spring force will do negative work. Why? Spring force is downward, displacement will be upward. And what is the upward displacement? Mg by k. So minus half k mg by k whole square. Okay, and the gravity force is also doing some work from this position to this position. What is the total displacement from this position to this position? 7 mg by k plus mg by k, which is 8 mg by k. So minus mg into 8 mg by k. Why did I do minus? Because gravity force is downward, displacement is upward. Okay, so minus mg into 8 mg by k. Understood? So out here, if I rearrange the equation, I'll get something around half mv square is equals to half k into 7 mg whole square is nothing but 49, not 49, 7 7 are 49, is m square g square by k square minus half k into m square g square by k square minus 8 m square g square by k. Okay, this is the, by this equation I'll find out the velocity. Now see, k and k square would get cancelled, k and k square would get cancelled. So this is nothing but, let me eliminate the k, n square, square and k. So this is nothing but, see out here, 49 minus 1. Okay, half into 48, this entire thing would be half into 48 m square g square by k, half into 48 m square g square by k, and 224 is nothing but 48, so 24 m square g square by k, 24 m square g square by k minus 8 m square g square by k is nothing but how much? 24 minus 8, 24 minus 8 is nothing but 16, so it would be 16 m square g square by k, 16 m square g square by k, or v square. See, v square would be, if I send this 2 to the right hand side, it would be 32, one of the m would cancel out the whole square, mg square by k. This is the velocity. If I want to write the velocity in terms of under root, it would be something like v is equals to how much? Under root of 32 mg square by k. Now 32 is not exactly divisible, square rootable. So 16 to the 32 or 4. I can take 4 root 2 to 16 4. I can take the 4 outside, no? See, 16 into 2 is 32. Okay, if you take 16 outside square root, it becomes 4. Understood? Now this is the velocity of topmost block as soon as the bottom block lifts up from the ground. Okay, so what is the velocity of center of mass at this point? Velocity of center of mass is nothing but mass of top block into velocity of top block root 2 mg square by k. Okay, plus mass of bottom block into velocity of bottom block by mass of top block plus mass of bottom block. M plus m is nothing but 2m. Now if I analyze this one, m and m would get cancelled. It would be 2 under root 2 mg square by k. Okay, now this is the velocity of center of mass at this point. Okay, velocity of center of mass is equals to this value. Now I can simply apply work energy theorem on the center of mass. Okay, because spring force becomes an internal force after this body lifts up from the ground. Okay, or I can simply apply v square is equals to u square plus 2s. Both of them have the same property. That means v square is equals to u square plus 2s is derived from work energy theorem. Okay, but change in kinetic energy is equals to work done by all the forces. So out here both are the same thing. Okay, it doesn't matter. So let me simply apply v square is equals to u square plus 2a into h or s. S is the height the center of mass rises from h2. Okay, see, if I apply half m, if I multiply this entire equation by half mv square, half mu square, and half 2 into 2as, half into 2s, 2 and 2 gets cancelled. So it would be mas, mass into acceleration is nothing but force, s is nothing but displacement, and force into displacement is nothing but work done. If you take this half mu square to the left hand side, it becomes change in kinetic energy is equals to work done by all the forces. So I already told you v square is equals to u square plus 2as is nothing but another term for work energy theorem. Okay, so I'm applying work energy theorem on the center of mass. So what is the final kinetic energy or final velocity as the center of mass reaches the topmost point? Okay, so the final velocity of center of mass would be 0. Okay, any body acting under a conservative force, okay, at a maximum limits, the velocities of those bodies equals to 0. Understood? What is the initial velocity square? Initial velocity square is nothing but velocity of center of mass whole square. It will be nothing but 4 into 2 mg square by k. Okay, or 8 mg square by k minus 2 into g. Why did I do minus? Because if I taken this velocity which is in upward direction to be positive, gravity acceleration due to gravity would be downward negative 2g s. I have to find out the value of s out here. The value of s out here is nothing but, see, 2 and 2 gets cancelled, g and g square gets cancelled. Okay, let me make this neat and clean. So s is equals to 4 mg by k. So out here s is equals to 4 mg by k. Okay, so from here, okay, after both the blocks has been lifted off, the maximum height of center of mass would rise by 4 mg by k. So center of mass would rise by 4 mg by k. 4 mg by k. Now the question is asking, okay, what is the maximum rise or what is the total rise of center of mass? Total rise of center of mass is nothing but center of mass, this maximum, this minus this one. So from here to here, it has risen by how much? From this position h1 to h2, it has risen by 4 mg by k, and from h2 to final point, okay, it has risen by 4 mg by k. So total rise or total rise in center of mass is equals to 4 mg by k plus 4 mg by k is nothing but 8 mg by k. Okay, so this is the concept that we apply in this problem. In this question, what has been given is that there are two bogies of mass m. On top of those bogies, there are two persons of mass small m. Now the first bogie is moving with velocity v1 towards right, whereas the second bogie is moving with velocity v2 towards left. Now when the bogies reach towards each other, what happens is this person jumped out here and this person jumped to the first bogie. Now as soon as this person jumps out of the bogie, it will carry the velocity of the bogie. Similarly, when this person jumps towards this bogie, okay, while jumping, it will carry the velocity of this bogie. Okay. So after this person lands on this first bogie, what happens? The first bogie comes to stop. So after this person jumps to this bogie, the first bogie comes to stop. That means this momentum and this momentum cancel out each other. And when this person jumped on this bogie, what happened is this bogie, the entire system traveled with v towards left or continued to move towards the same direction as v2 with velocity, new velocity v. The question is asking, find out the velocity v1, v2 in terms of capital M, small m, okay, and v. So we must apply conservation of momentum. No, see, one thing you must understand: conservation of momentum and conservation of velocity of center of mass is the same thing. Okay, see, in velocity of center of mass, what is velocity of center of mass? m1 into v1 plus m2 v2 divided by m1 plus m2. Now, if you multiply this m1 and m2 to the left hand side, it is m1 plus m2 into velocity of center of mass. No, understood what was happening? In the right hand side, we get conservation of momentum, whereas in the left hand side, it is m1 and m2 into velocity of center of mass. Okay, so velocity of center of mass is derived from the same principle of conservation of momentum. Okay, let's focus on this question. Now we must conserve our momentum between these two parameters. Now what are the systems that we must take? See, this person jumped on this body, no? So can I say there is no external forces acting on this direction? If there is no external forces acting on this direction, let me consider this bogie plus this person as a system. Okay, this bogie and this person as a system. So initial momentum of the system will be equals to final momentum of the system. Understood what I'm trying to do? This mass and this person is a system. So system 1, for system 1. System 1. Okay. If I apply conservation of momentum, what was the initial momentum? mv1 minus mv2. Why minus? Because whenever you are dealing with velocity, always assign the coordinate system in every problem. Okay. So initial momentum is equals to capital M into v1 minus small m into v2. Okay. What is the final momentum? M into 0 plus capital M into 0 is equals to 0. Okay. So from here I can get the relation mv1 is equals to mv2. This is our first equation. Okay. You can also apply the conservation of center of mass, or velocity of center of mass will remain constant, okay, between these two bodies. This is the same equation as this one. Understood? Now I'll take system 2. What is system 2? This person jumped on this bogie and became this one. So this person and this bogie is considered as system 2. So let me conserve the momentum. Small m into v1. minus capital M into V2. This is the first initial momentum of this system 2, and final momentum is nothing but capital M plus small m into minus B. Why? Because both of them are moving with same velocity towards negative velocity direction with velocity minus B. Understood? Now if I multiply this minus with this equation, what do I get? I get something like capital M V2 minus M V1 is equals to M plus M into V. Okay. Now I must either replace this V2 or V1 from this equation. You can replace any one, you can find out the other. So replace V1. V1 is equals to small m by capital M into V2. So if I write this equation out here, M V2. What is V2? Sorry, let's replace V1. M V2 minus small m V1. What is V1? Small m by capital. If I send capital M to the right, small m by capital M into V2. Small m by capital M into V2 is equals to m plus m into V. Okay. Now from this one, I can take V2 common. V2 is equals to how much? Let me just solve the equation out here. V2 is equals to how much? Let's take V2 common. Now if we take LCM out here, what will happen is capital M square minus small m square divided by M. We just took LCM out here. Okay. And V2 is equals to M plus small m into V divided by M square minus small m square into M. See, now this A square minus B square can be written as M plus M into M minus M. Okay. So if I write this as M plus M, one of the M will get cancelled and it become M minus M. Okay. This can be expanded as M plus M into M minus M. And M plus M and this M plus M would get cancelled and the remaining parameter would be M minus M. So out here, V2 is nothing but capital MV divided by M minus M. Similarly, when I apply the same equation, see, V2 is equals to MV by M minus M, no? What is V1 equals to? V1 equals to small m by capital M into V2. So V1 is equals to small m by capital M into V2. What is V2? MV by M minus M. Out here, M. Or V1 is equals to M into V by M minus M. Now see, the direction of, see, I have considered V2 in this direction, no? And V1 in this direction. So when I'm giving this, these are just the magnitude. V2 will be in negative direction, V1 will be positive direction, and the magnitudes will be this one and this one. V2 is equals to mv by m minus m, V1 is equals to small mv by m minus m. So this is our problem. In this question, what is happening? There are two bogies, okay, both of same mass, and they're moving towards right with velocity v0. The first bogie or the back bogie has a person of mass m. Now this person decides to jump on the first bogie at certain instant. So as soon as he jumps, what happens? Okay, as soon as he jumps, the velocity of this bogie changes from v0 to some other velocity, no? Because as soon as he jumps, he's imparting some momentum out here. Okay, and he's imparting some impulse out here, and that will change the velocity v0 because he's slowing it down. Then only he can jump, no? Okay, because if he jumps upward, what will happen? See, relative to the ground, if he jumps, okay, if he jumps, this bogie will slow down. Okay, and after slowing down, the velocity became vr, and the velocity of the person is nothing but given as u. Okay, this u is seen by someone sitting on the bogie. Okay, that means this person, this u or this velocity of the person is observed by someone sitting on the bogie. Now to apply conservation of momentum, we need to shift off or write down all the velocities to a single frame. Okay, So this velocity was written in terms of frame of reference of ground. This velocity was written in the frame of reference of ground. This velocity is from the frame of reference of ground, but this velocity is from the frame of reference of this body. How do I convert this frame of reference to the velocity of ground? See, this u is nothing but velocity of the frame. So if I want to convert this velocity to the velocity of ground, it will do nothing but u plus vr. Okay. See, if you apply simple relativistic mechanics, you can get this value u plus vr. Or even if you backtrace it means from this frame of reference, the velocity of this person is u plus vr. So if you change your frame of reference to this moving frame of reference, it will be vr in this direction. So u plus vr minus vr becomes u. Understood? So I've converted the velocity of this person from the frame of reference of this ground. Now this person, okay, and the first bogey was literally moving with velocity v naught, okay, and this person will land on this bogey, okay, and after he lands on this bogey, the velocity of this bogey will also change, okay, because he is carrying some momentum, different momentum. So the first part of the question is find out the velocity of this bogey after he jumped. So let me apply conservation of momentum out here and out here, because there is no, if we consider this person and this mass as a system, there is no external force acting on this system, no, okay. So initial momentum is equals to how much? Initial momentum is equals to m plus m into v naught. Final momentum is equals to how much? M into vr plus small m into u plus vr. M into small m into u plus vr plus capital M into vr. I need to find out the value of vr. Okay. So if you isolate the equation, capital M plus small m, let me write down the equation. Okay. Now I can take vr common from this part. Now if I send this mu to the left hand side and divide this by m plus m, we'll get the answer. So this is the velocity of the first block after the person has jumped off. Now what I need to find out is the velocity of the second block after this person has landed on this block. So after this person has landed on this block, okay, after this person has landed on this block, the velocity of this block would change because this person is imparting some velocity onto this block. So if you take this entire person plus system as a person plus block as a system, okay, the momentum of this system would remain conserved. That is the advantage I got while transferring or making this velocity relative to the ground. If I consider this as a system now, okay, so the momentum of this entire system will be equals to momentum of this entire system after the jump. So m into v naught plus small m into u plus vr is equals to m plus m into v1. Now what I need to do is substitute the value of vr from this position to this position, and I'll get the answer. So I've just substituted this value of vr from this position to out here. Okay. Now if I multiply this u by m plus m, that means I'm taking m plus m as common LCM. Okay. It will be capital Mu plus small mu. Okay. Now this small mu and this small mu will get cancelled. Okay. So when I simplify this one, it would be nothing but say v1 is equals to v naught plus m mu by m plus m square. What I did out here is take this m plus m common LCM throughout. Okay. So this will be multiplied by this one, capital M into m plus m. Now send the entire thing to the denominator. This m plus m and that m plus this m plus m and that denominator would get cancelled. Okay. Out here. Okay. That means I'm taking this m out here and then separating them both. Okay. So what will obtain is this value. Just do the calculation of yourself. This is simple algebraic calculation. Similarly, you can simplify this as, see, if you divide m plus m by m plus m, this is nothing but v naught minus mu by m plus m. okay, is equals to VR. Acha, this question is more or less similar based on conservation of momentum. Okay, so in this question, what is happening is there is a bogey out here, and there are two persons out here. Okay, person 1 of mass m and person 2 of mass m. Now the first question is saying both of this person jumps from the bogey with velocity u related to the bogey. So what is the back velocity of this bogey? The second part of the question is asking the first person jumps with velocity u related to the bogey. After that, the second person jumps with velocity u related to the bogey. Then what will be the final velocity of the bogey? Okay. So let us solve the first case. Okay. For the first case says that both the person jumps off from the bogey at the same time. That means this person of mass m jumps with velocity u. Okay. And even this person, the second person also jumps with velocity u. Now this velocity u is seen by whom? The velocity u is seen by this bogey, no? Okay. And one more logic. If this person jumps off the bogey with certain velocity, the bogey will also fall back with certain velocity, no? So let that velocity be v naught. Okay. Now see, in order to apply conservation of momentum, all our velocities should be off from the same frame of reference, isn't it? I cannot apply this from this frame of reference and this velocity from ground frame of reference. If this velocity is from ground frame of reference, the velocity of this person should also be from ground frame of reference. Understood what I'm trying to do? I'm trying to convert all my velocities from a single frame of reference. Okay. So this velocity or this v naught is seen by someone on the ground. So how do I convert this u from someone on the ground? We just add the velocities of the frame. So someone on the ground will see this person moving with u minus v naught and this person moving with u minus v naught. So this u minus v naught is nothing but velocity seen by someone on the ground. Now we can simply apply conservation of momentum. What was the initial momentum out here? The initial momentum was total mass m plus 2m into what was the velocity? 0. See, none of them are moving, no? So the total velocity of the system is equals to 0. Okay, what is the final momentum? Final momentum is whenever dealing with momentum, always as a coordinate system. Okay, minus mv naught plus m into u minus v naught plus m into u minus v naught. Okay, now if I solve this equation, this left hand side will be 0. I need to find out the value of v naught. So let me find out the value of v naught. I just couple these two together. Okay, this becomes 2m u minus v naught. Now I can send this. Acha, let me expand this one and take v naught common. Then I'll send everything to the left hand side. So in our first part, okay, the v naught or the velocity of this bogey is nothing but 2mu by m plus 2m. And observe one more thing in your entire mechanics or entire physics. Whenever you take the sign inside the equation, no, okay, the result just gives us the magnitude of the value. That means although I know that v naught is in this direction, it just gave us the value, no? So whenever you're taking sign inside the equation, okay, you're taking the sign inside the variables of the equation, then the value, then the variable or the output will give us the magnitude. Okay, now the second part of the question. The second part of the question is asking the first person jumped up with velocity v, sorry, velocity u. So when the first person jumped with velocity, what happens to the bogey? The bogey will rebound with velocity v1, and this u is relative to this velocity, this bogey, no? So if I shift my frame of reference to the ground, what will happen? The velocity is nothing but u plus v1, sorry, u minus v1. Why is it is minus? Because u and v1 are in opposite direction. So u minus v1. Okay. Now if I apply my conservation of momentum in this bogey and this bogey, what will happen? See out here.
total initial momentum was equals to 0 because nothing was moving out here, no? So m plus small m into 0 is equals to 0. And out here, what is the momentum? Take account of positive and negative. So it is minus mv1 plus m, which is the mass of the person, into u minus v1. Okay, now I need to solve for v1. Acha, I made a little bit of error out here. Okay, see out here. I made m into v1, no? But this person was also along with the bog, you know. So it would be capital M plus small m into v1. So I'll be erasing this one, minus capital M plus small m. Why small m? Because this person was also in the boggy when this person jumped off. Okay, and then I'll solve for v1. So if I see the value of v1 after the first person jumps off is m into u by m plus 2m, for capital M is the mass of the block and small m is the mass of the person. Then after this, what happens? See, after this, the second person also jumps off from the bogey with velocity u relative to the bogey. Okay, and as soon as this person jumps off, what happens? The velocity of the bogey also changes. Let the velocity of the bogey be v2. Okay, now I must change this velocity from the frame of reference of ground. And how do I do that? U minus v2. Okay, now I must apply momentum conservation between which two bodies? Between this body and this body. Because out here, this body already flew off, no? And I already got the value of v1. I already got the value of v1 out here, isn't it? So this entire system was moving with v1, and after this person jumped off, this velocity became v2. So I must take this as a system and this as a system. Both these systems are same thing. Okay, so initial momentum of this body and final momentum of this body will be same because there is no external forces on this direction. Let me draw the equation. What is initial momentum? Minus m plus m into v1. Why minus v1? Because v1 is in negative direction, is equals to minus mv2 into plus m u minus v2. Now I out here I must substitute this v1 out here. Okay, this value would be substituted out here. So it would be nothing but minus m plus m into mu by m plus 2m. Asha, I'm just solving this equation. You will just follow it through. Okay. What you do out here is, see, you expand this one. Okay. Isolate v2 and send this mu to the left hand side. Then do means take m plus 2m as LCM and simplify the numerator. Then take v2 common. Okay, and multiply it at the bottom. So in this question, what is happening is somebody is holding this chain. Okay, this chain is held by a thread out here in top of a table. Now the question is saying, show that if the thread has been cut off, what will happen? The chain will drop on the table. The question is asking, show that when the chain is dropping on the table, the force exerted by the table, that means the force exerted by the chain on the table, is double that of if the chain was already resting on the table. That means the force exerted by the chain on the table out here is double that of force exerted by the chain on the table out here. Out here, what is the force exerted by the chain on the table? Mg. An equal and opposite reaction force would be the normal force. Okay. So the question is asking, show that while dropping, the force exerted by the chain on the table is 2 mg or twice of mg. And how we do that? See, let's take an element out here. Element means let's take an elemental length x dx of the chain. Okay, now this will drop from length x. Okay, I'm taking an elemental length of the chain out here. Okay, and this will drop out here. What is the velocity when it reaches the ground? The velocity when this elemental reaches the ground, or elemental length of chain reaches the ground, is nothing but under root of 2gh or 2gx. Okay, if you take the element out here, the velocity of the chain would, as it reaches the ground, would be under root of 2gx. Fair and fine. So the question is asking about force, and how do we relate force with velocity? See, I can simply say force is equals to rate of change of momentum, no? dp by dt. And what is momentum? Momentum is nothing but product of mass and velocity. Okay, so if I open up this bracket, force is nothing but m dv by dt plus v dm by dt, isn't it? Now check out here. The velocity of the any element, okay, as it drops down will be constant. That means the maximum, not maximum, all the force interaction is happening after the chain is touching the table, no? So this element, okay, will exert the force on the table only after this element touches the table. Okay, so doesn't matter which element you take, the velocity of all the element would be under root of 2gx, isn't it? So dv by dt is out here 0. This much is understood. Okay, why I'm making this dv by dt is equals to 0? Because doesn't matter which element of the chain that you take. Okay, the velocity would always be a function of x, and it will always be under root of 2gx. After hitting the table, it stops to 0. That's fair and fine. But the velocity at out here, it won't be changing, no, with respect to time. It will be changing instantaneously to 0. Okay, now after that, what is the value of v? The value of v is nothing but under root of 2gx. Now you have to find dm by dt. Dm is nothing but the elemental mass of this chain out here. Elemental mass of this chain. Okay. Now if I consider the entire mass of this chain to be m. See, entire mass of this chain to be m. Okay. And entire length of the chain to be L. So if I apply unitary method, m mass contains L amount of length. Okay. So unit mass will contain, or unit length will contain, let's not make this in terms of mass, let's make this in terms of length. Unit length will contain m by L amount of mass. Just unitary method. 5 mangoes cost 10 rupees. 1 rupees will give 5 by 10 mangoes. Similarly, L length of chain weighs m mass. So unit length of chain will weigh m by L mass. So dx length of chain will weigh m by L into dx. Okay. So this much amount of chain will weigh m by L into dx. So it is nothing but d. What is dm? Dm is nothing but m by L into dx. M by L into dx divided by dt. Okay, dm out here is substituted by this value, and this value we got by unitary method. Okay, now look at this. M is constant, L is constant. What is dx by dt? Dx by dt is nothing but velocity of the object. Okay, under root 2gx into m by L into v. Why? Because dx by dt is velocity. Okay, this dx by dt is velocity. And what is velocity? Velocity is nothing but under root of 2gx. So is equals to under root of 2gx into m by L into under root 2gx, which is equals to under root 2gx square into m by L, which is equals to 2gx m by L. So this is the question, or this is the force exerted by the chain on the table. Now the second part of the question, how do I prove this is twice of this value? What is the force exerted out here? Stay out here now. One more thing. At x is equals to L, that means when x is equals to full length, what will happen? If you substitute x by L, what will happen? If I substitute this x by L, what will happen? This will become 2m into g, where m is nothing but mass of the whole chain. Okay, see the force exerted out here by the chain on the table is equals to 2mg. Similarly, what is the force exerted by the chain out here? Mg. So I proved that force exerted by the chain on the table out here is double that of this value. Okay, because force out here is mg. Okay, this kind of questions, acha, this kind of question is there in HCV also. I forgot the question number, but it is there. Okay, so just these are just playing with equations. Okay, so these are not very important kind of questions in terms of JEE. So just see the question and memorize it as it is. Okay, because few doubts you must have out here. Okay, how does force exert out here? Because there is no parameter of time given. Okay, similarly there should be impulse, no, instead of force out here. So this kind of question just these are just equative questions. That means the equation is seen as it is. Understood?